So we've talked about one extreme case already, and I started to introduce the second one, but let me go back and remind you. The first extreme case that we dealt with is where the halide is leaving and the nucleophile, that is, it's breaking its bond with the tetrahedral carbon, and the nucleophile is making its bond with the tetrahedral carbon at the same time. And ideally what we're talking about is that when the carbon-halogen bond is half broken, the carbon nucleophile bond that's forming is half made. So that's the extreme case. Everything is happening at the same time. It's a concerted reaction. We call that an SN2 reaction. In the other case, the bond between the carbon and the halogen, that's the leaving group, that happens first, and it happens completely. That's an SN1 reaction. So that's a substitution. It's also a nucleophilic. We substituted the halide for a nucleophile. It is unimolecular in that in this particular case the rate of reaction is only going to be dependent on the concentration of the alkyl halides. The rate equals a rate constant times the concentration of the haloalkane. And I want to mention to you that that rate constant K is not the same number as what we saw for SN2. Every reaction will have its different K. And that K will be different depending on what the haloalkane is, what the solvent is, if in the case of the SN2 reaction, what the nucleophile is. So it will be dependent on everything that's there, and there will be a different K for every reaction. So let's talk about the SN1 reaction. In this particular case, again, SN1 reaction, we break the carbon-halogen bond first. We break it heterolytically. This means that one of the atoms is going to carry away 2 electrons from the 2 electrons that were bonding between the 2 atoms. And the other atom gets no electrons. And so this is not a homolytic breakage where we'd get 2 radicals. It's a heterolytic reaction where we get charged compounds. We get the charged intermediates like the carbocation and the bromide that are shown. So this is typically a slow reaction. For that to occur, we have to break the carbon-halogen bond, and that has some stability, and so that doesn't occur. It doesn't occur rapidly, spontaneously, so it occurs slowly. And it gives us a carbocation intermediate, which is shown at right. And in this particular case, it's a tertiary carbocation intermediate. Notice that that carbocation is sp2 hybridized, and so there's an empty p orbital there that can accept 2 electrons, we're going to see later on. But that's a trigonal planar carbocation rather than the tetrahedral geometry of the starting material. And in the next slide, we see how that trigonal planar carbon can react. It's using its MDP orbitals can react with the nucleophile. So the nucleophile in this case is methanol, CH3OH, and the nucleophile can either come in from the left side or come in from the right side. If I was drawing the arrows, by the way, those red arrows that are shown there, I would draw the arrows to the lobes because those pair of electrons are going to bind to that carbon, but they're going to bind to the lobes of that carbon in order to make the new bond. But that's not really a big deal. So in any case, I should point out too that there's a plus and minus to the upper right-hand side of that carbocation. That's incorrect. This is a positively charged carbon, so there should be only a plus charge there. So that's a little mistake from the book manufacturer. But the methanol can react from the left side to make a new bond or the right side. If the methanol reacts from the left side, we're going to move the 3 methyl groups that were on the carbocation to the right in order so that everything is tetrahedral when we're done. And now we should have a positive charge on the oxygen. And actually, I'll probably correct those before you guys see this. So you may not see plus and minus. Hopefully, you'll see just plus. But in any case, if the oxygen of the methanol comes in from the right side, then the 3 methyl groups are going to migrate to the left. And so we see the 2 structures of those. But in this case, the structures are identical, and so we can't tell the difference between these 2 structures. We say they're identical; they make the same product. So in the last step of this reaction, after we've made the carbon-oxygen bond, we have a protonated ether. Protonated ethers are very acidic. What are the pKa's? You should know that. That bottom equation at the back is an acid-base reaction, and so if you would analyze it, you would say, oh, protonated ether on the left, protonated alcohol on the right. Both of those pKa's are going to be, though they're very acidic acids, protonated alcohol or protonated ether or protonated alcohol, they're both going to want to give up the protons. And the pKa's of those are -2, and the KEQ is going to be about 1. But let's assume that we've added a whole bunch of methanol in this reaction, not just one equivalent. And so if we add a whole bunch of methanol, that means the concentration of the methanol left is going to be very high. So Le Chatelier tells us it's going to push the reaction to the left. So the product of this substitution reaction is going to be deprotonated. It's going to be mostly deprotonated because of Le Chatelier. The energy diagram for this kind of process is as follows. In the first step of the reaction, we're going to be losing the carbon-bromine bond, and I want you to think about what that transition state for that reaction is going to look like. We make the carbocation intermediate after breaking the carbon-bromine bond. That's shown as the energy well between EA1 and EA2. And then after it loses the bromide, after it becomes the carbocation, then it reacts with the methanol, so we make a new oxygen-carbon bond. You should think about that transition state as well. I want you to be able to draw these based on the transition states, rather, based on what you know about the starting materials and what you know about the intermediates. So I want you to be able to draw these, and you should think about that before we get to class on Tuesday. So in any case, we make that substitution product. In this case, the substitution product is protonated. It will still undergo a proton transfer reaction, as shown in the last slide, where if we have a lot of excess alcohol, we're going to drive the reaction towards the protonated alcohol, and we'll get the product ether. This is the product of the substitution. We're going to get that primarily. And so this is what the energy diagram looks like. It's got two humps. It's got a carbocation intermediate, we have this as exothermic. And again, remember the carbon-halogen bond is fairly weak, whereas the carbon-oxygen bond is fairly strong. We also talked about how stable the Br- is, and so so in this particular case, we should, in all the cases where you draw the energy diagram for the SN1 reaction, you should have it exothermic overall. Here's something that happens when we make carbocations that we have to be thinking about. So in this particular case, we have a secondary bromide. By the way, secondary bromide, that's a bromine on a carbon that's a secondary carbon. It's bonded to two other carbons. Notice for this secondary bromide, on the right side we've got a methyl group after making the carbocation, and on the left side we've got a tert-butyl group. And so if we make a secondary carbocation, and if we can migrate a carbon or a hydrogen, we're going to see later on, with the pair of electrons. So in this case, we're migrating a CH3 with its pair of electrons. They're just going to migrate over, and we make a tertiary carbocation. Tertiary carbocations are more stable than secondary carbocations. So in fact, this is a favored process. We'll make tertiary carbocation in greater amounts than the secondary. And so now the nucleophile, which is ethanol, that will react at the tertiary carbocation to make a new bond, and then we're going to lose the proton on that ether by the same acid-base reaction that we talked about earlier. So it's possible that if we can make a more stable carbocation, that we can migrate pairs of electrons, and we should be thinking about, we can migrate an alkyl group, in this particular case a methyl with its pair of electrons. We should see a couple of examples of that in class, and remind me to give you a couple of examples if I don't recall. There is a unique feature of an SN1 reaction that we need to be aware of, and that's the possibility that we can get a racemic mixture. So in this particular case, we've got a secondary alkyl chloride, or chloroalkane. Either of those is correct. Now we pop off the halide, which is the first step in the SN1 reaction, and we make the carbocation intermediate shown. So that carbocation intermediate can react with methanol from the left side to give the product on the left side, or it can react with the carbocation on the right side to give the product that's shown on the right side. Those two products are enantiomers of one another. Anytime you make a product, the first thing you should think about is, am I making a stereocenter? If you're making a stereocenter for one of these kinds of reactions and there's no chiral centers anywhere else in the substrate, or there's no chiral centers in the nucleophile, and that's the case in here. So we started with zero chiral. We started with rather the R enantiomer of the alkyl chloride. And in this particular case, we make a mixture of R and S SN1 substitution products. So we racemize. Remember, racemic is 50-50 mixture. Here we're making, we typically don't make exactly 50-50, but for this class you should say we make a 50-50 mixture of the S enantiomer and the R enantiomer if the halogen leaves from a stereocenter. So every time the halogen leaves from a stereocenter, it's going to make an sp2 hybridized carbocation intermediate that can be reacted from either of the lobes of the empty p orbital to make the two enantiomers. So you have to give that some thought. So in the next few slides after this one, we're going to talk about some of the experimental evidence for why we think these two mechanisms exist. And we're going to look at the evidence for this. And I would say that for an organic chemist, what we say is that not necessarily that we know the mechanism, but that all of the data and all of our experiments have been consistent with the existence of these mechanisms. So in fact, we can't see this reaction occurring. Maybe someday we'll be able to do that. We can't see it occurring, but the experiments that we've devised to figure out how it's working are consistent with our interpretation. So we're going to look at the structure of the nucleophile and the structure of the electrophile. That's the haloalkene. We're also going to be looking at the structure of the leaving group and how the solvent interacts with either the starting materials or the intermediates, the carbocation intermediates in the case of SN1 reactions. Remember, SN2 reactions have no intermediates, but we're going to look at those issues.